Okay, let's talk about the multiplication and division of power series. Now, before we get into this, I want to talk about something that I wish I would have been a little more explicit about in the preceding videos for this section and the previous section. But okay, we've seen examples where we have a power series or even like a function. So like, for example, we have like a function, some function of x is equal to its power series representation. So it's been proven that they're equal. I'm just going to make this a Maclaurin series. So a is 0, but this could be centered anywhere, you know. And we've seen examples where we multiply some x expression on both sides. So like we'll say maybe x or x squared and then put x here. And then we're left with and then we bring the x into the a sub n formula and you get, right? We did things like we might have had x to the fourth over 1 minus x. And then we wrote that as, we did this in the previous section. And then we got the power series representation for this, the geometric series with first term 1, and then we brought in the x to the fourth after that. Okay, what I wish I would have pointed out is that, so yeah, when you multiply two, like the two functions like this, you multiply something by the power series, the only thing you can multiply a power series by, and then the result is ends up being a power series, is going to be some power term, like x to an integer power. And I want to say you could also technically multiply any polynomial, like, you know, ax squared plus bx plus c, like the general form. You could technically multiply any polynomial, and if you know, it might be a challenge to simplify it to show that it's, even in that case, it's still, you still have a power series. Again, depending on the order of the polynomial and how many of the coefficients aren't 0, it could be tough to show that it still is a power series officially. But you know, any power term or polynomial that you multiply by a power series and you simplify, what you get is a power series for all n, from the starting n to the original starting point to infinity. Now, I did mention examples where, so, you know, we talked about how, well, what if could you do something like 1 over x to the fourth? Times, okay, and we actually did this multiplication. You can absolutely bring this in and simplify, and what we saw was that what ends up happening is it's not a power series, anymore. And the reason is because you have, so this would be, this is c sub n x to the n minus 4. And so it's not a power series because for n is equal to 0, it's x to the minus 4. That's not part of the definition of a power series. In reality, you could write it this way. From n is equal to 0 to 3, c sub n x to the n minus 4 plus, no, this would be, okay, when you write it this way, this is a power series, but this isn't. Now, when you combine these two, then the net result is it's not a power series. However, though, like this is equal to this, and this is equal to this. This is valid here. This is correct. These three are equal. In fact, you could multiply power series by any function of x and then bring it in and simplify. We could multiply by sine of x, and bring it in. Every term would have a sine of x. Now you just have to combine the domains. The domain's going to change based on the combined domains of the two, but you could do that. However, though, what you can't do, or at least we haven't proven anything like this to be true, you can't say that, so okay, cosine of x, it's Maclaurin series, okay, You can't do this. You can't say, okay, we're going to multiply both sides by 1 over x to the 4th. No, you can't do this. And so why not? So that means we can't multiply the power series by 1 over x to the 4th? No, we just showed the mechanics of doing that. You can do that. However, we can't say that this comes from the fact that the problem is the power series being equal to its function issue, right? We proved that cosine of x is equal to this. We proved that. Now, if we multiply both sides by something, that's valid. We know we can do that. And then the result is, after you simplify, you get a power series, then nothing's changed. However, when you do this, the result is not a power series. And we haven't talked about that yet. I'm not saying maybe this is true. I don't know, but we haven't talked about that yet. Now, what you will get, we just saw, was that you can separate out like the first 3 terms. That's not a power series, and then plus another power series. Well, if you want to go from there and go test that power series on your own, test to see if so you would compare. I'm not sure if you could do that either. Yeah, so I'm not even going to go there. You just can't. We haven't learned anything about this yet. This is not a power series anymore. However, though, again, the mechanics of actually doing this here, you can multiply a power series by any function of x and get another series, and that's correct, assuming there's no, you've accounted for any domain issues, like every coefficient exists and all that. Okay, and so that's the reason why all the example problems that we've worked in the textbook, when we multiply some like function of x by a certain function in power series, it's just been like x to an integer, positive integer power. Because then when you bring the x in, you just left with another power, and you simplify, you just left with another power series. And that's the reason why, if you look here, so you have sine of x is equal to its power series. We have the power series for sine of x. If you want to find the power series for e to the x times sine of x, you can't just multiply both sides by e to the x, because yes, you could multiply e to the x by a power series, combine and simplify, and that's valid. But you can't say that they're equal. You can't say e to the x sine of x is going to be equal to that. You can't officially say that in regards to the concept of proving that a power series is equal to a certain function. Okay, so what can we do, though? Is there any way, dealing strictly with power series, that we could think about what the power series of e to the x times sine of x is without having to, go through the whole derivation from scratch? Yes, what we can do is we can think about multiplying the power series representation for e to the x by the power series representation for sine of x. Okay, so if we can multiply these two power series, then we can get the power series representation for e to the x sine of x. So the question is, how do you multiply power series? Well, okay, the rule is that as far as multiplying power series, it's the exact same concept as multiplying two polynomials. Right, a power series is a polynomial. It's an infinite polynomial, and an infinite degree polynomial. So when you're multiplying two power series, it's the exact same concept. It's like an infinite polynomial distribution. 1 times this, times this, times this, times all the infinity terms, plus this times the first term, times the second term, times the third term, times all infinity terms, plus this times the first term, times the second term, times the third term, times all infinity terms. That is exactly how you think about the multiplication of two power series. Again, a power series is always it's a polynomial. Every power series is going to be it's an infinite polynomial. Okay, so but how do we kind of mechanically apply this? All right, well, I like the method that they show here. I think this is a really good method. Okay, they write out, so here's the first polynomial, so that's e to the x. 1 plus, you can see that's x plus 1/2 x squared plus this 3 factorial is 1/6 x cubed plus ... And you can think about, though, if you might want to include more terms. The whole idea is you want to be able to, once you do the multiplication, what we're going to do is we're going to kind of do the multiplication for the resulting multiplication for, like, we want to see the first 5 or 6 terms or 7 terms of the resulting multiplications, and then see, the idea is you ideally want to get see a pattern with that. Okay, and so to do that, they write out, so here are the first 4 terms of e to the x, but you could do more. And then the second polynomial, they match up like so. Okay, we've got x with sine of x, it's like the x to the first, then x cubed, then x to the fifth, etc. So there's no even exponents on the x term. So they put x vertically aligned with the corresponding first order term with e to the x. They put x cubed aligned with the corresponding x cubed term on e to the x. And they would do the same thing if there was more terms. Okay, so you're multiplying two infinite polynomials here. So you're just going to have 2 rows. Then you draw a line. Then what they do here is they go to the first term for the second row polynomial. They go to the first term that's there. And then in this entire row, this is, okay, x times 1 is x. X times x is x squared. X times 1/2 x squared is this. X times 1/6 x cubed is this. And they do that plus that plus that plus that plus dot, dot, dot. The next row, they come to this term and do the same thing. Minus 1/6 x cubed times 1 plus minus 1/6 x cubed times x. But then they write those out, but they still line up the order of the terms, even here. Okay? But the difference here, though, is that you might have, if there's a term here and a term here, let's say there was a term here and a term here, then you'd have 4 rows before you got to this line. Before you put another line, you'd have 4 rows. Okay? But again, I want to stress that they're still lining up the order, the order of the terms. That's important. Even here, definitely here it's important. Okay? So they're lining up the order of the terms. So once you have however many rows here, you put a line. And then since those terms are ordered like that, they're lined up, you add up this column, add up this column, add up this column, add up this column, and you get this. Okay, and that's the resulting, this is the multiplied, the initial terms of the multiplied, the multiplication. And you can think about if you extended this out a little bit more, then you would have, this would be extended out, you'd have more rows here, but then you get a longer term here, okay? And so then e to the x times sine of x is equal to this. And ideally, there would be a pattern that you would see here, and you could put this into a summation. You could write an a sub n and put it into a summation, or maybe there's not. Just depends. But still, that's the infinite series for e to the x times sine of x. It's, x plus x squared plus 1/3 x cubed. I'm not sure why they didn't do more terms, but, it looks like you could, if you did 2 or 3 more terms, you could see what the pattern is for the coefficients. But it looks like it's going to be x, like an x to the first plus x squared plus x cubed plus x to the fourth plus x to the fifth with some coefficients that you need to get a formula for. Okay, so that's how you can multiply 2 power series. What about dividing 2 power series? So if we want to get tangent x, we know that's sine of x divided by cosine of x. Now you could do this from scratch, but maybe we could divide sine of x by cosine of x. So how do you divide 2 power series? Well, any power series is a polynomial, so we're going to do this using polynomial long division. So if you need to review the principles of polynomial long division, we learned that in algebra. So in the algebra playlist, we go through polynomial long division in full. As of this moment, I haven't gotten to that section yet, but I'm very close. So those videos should be posted in the algebra playlist pretty soon. But you can see here, all they do is they write out however many terms of, in the numerator polynomial they want to include, and similar with the denominator. And just the more terms you use, then the more terms the final division is going to come out with. But one thing you might notice here is that they've got the polynomials, the dividend and the divisor. The order of the polynomial is in increasing order. So x to the first, then x cubed, x to the fifth. Well, and that makes sense. That's how the power series are ordered. But in polynomial long division that we learn in algebra, the polynomials are in decreasing order, like you write a typical polynomial in decreasing order. Now, it's not a big deal. The mechanics are still the same. We'll do this division in a second. It's just the same mechanics as regular polynomial long division. But I've done some investigating to try and see if how we can divide in reverse order like this. Because if you come off to the side and do just a regular standard polynomial long division problem that we would learn in algebra, you get the answer. And then if you do that same division, but you reverse the order, you don't come out with the same answer. So I'm still doing some digging to try and get some answers on why the polynomials are in increasing order like this. I mean, obviously, I know why you can't put them in decreasing order, because you can't put the infinite term first. So I get it, but I'm just curious as to why it ends up, why the division is valid when in regular polynomial division we don't do it this way. One thought though is that we can think about with power series. For a power series to converge, each successive term is getting smaller and smaller and smaller. If that's not the case, then it's not going to converge, right? And so we're always dividing power series or multiplying power series that are convergent, right? The convergent sine of x divided by the convergent cosine of x. And so with that, it makes more sense in that, when we divide polynomials, you're really putting the highest magnitude term first, right? It's like when you divide regular numbers, 500 divided by whatever, 5, we're starting with the hundreds place. Then we go down, then the magnitude gets smaller. So in this sense, this is the highest magnitude position. However, though, okay, that's fine, but all right, so if I'm dividing x to the 5th plus 3x squared plus 2 divided by x minus 7, well, okay, but it depends on what x is, right? Maybe if x is less than 1, then x to the 5th is smaller than 3x squared. So if x is between 0 and 1, a decimal, then x to the 5th is less than 3x squared. So I don't know. I'm doing some investigating on this. And so check out the example problem videos on dividing power series. If I find an answer, I'll talk about it in one of those videos. But okay, so polynomial long division, what you do is, so you're going to divide x here, this first term in the dividend, by the leading term in the dividend. You divide that by the leading term in the divisor, and then so that's x divided by 1 is x, and you're going to put x to the first above the corresponding power. Like, so if we got x cubed, we put it right here. So you line up the powers. Now, typically we would, with polynomial long division, we would put like a placeholder 0x squared and 0x to the 4th, and you put like a placeholder here 0x cubed and 0x, but you technically don't have to do that, but just keep that in mind that they're omitting those placeholders. So okay, you get x up here. After you do that, after you divide x by 1, put x here, then you multiply x by the divisor. So you get x times 1 is x, and then so x times minus 1/2 x squared is minus 1/2 x cubed. But let's say that you would need a placeholder potentially if you had if this was just x to the first. Then you'd get x times minus 1/2 x is minus 1/2 x squared. Well, then you need to line that up with the placeholder 0x squared. So depending on the problem, you might have to put placeholders in the divisor and dividend, which is not that big of a deal. Okay, so then they do 1/3 times 1/24 x to the 4th, line that up here with the x to the 5th, and then you subtract these two, and it's always the case that the first term goes to 0. Now you're left with this. Then you divide, so 1/6 plus 1/2 is 1/3. Then you do 1/3 x cubed divided by 1 is 1/3 x cubed. You put that above the x cubed. Then you multiply that times the divisor, and you get this. They subtract those two, you get this. Then you divide this by 1, put that up here, and then they stop there. So there are the first 3 terms, and they just write out the first 3 terms with 3 dots. And as far as like the remainder, which would be whatever you're left with here divided by the divisor, with division of power series, you don't have to consider that. You just generate however many terms you need up here, and that's you look at that as the division. Okay, it says, although we have not attempted to justify the formal manipulations used in the example above, they are legitimate. There's a theorem which states that if both f of x, so a power series and another power series, converge for some radius of convergence r, and the series are manipulated as if they were polynomials, then the resulting series also converges for that same radius of convergence and represents f of x times g of x. Okay, what they're saying here is when we multiply two power series, then we can think about the radius of convergence doesn't change, assuming they both have the same radius of convergence. If they have different radiuses of convergence, then it doesn't tell us anything about that. And then, okay, for division, we require that the first term, the b sub 0 term, b is, so what are they talking about there? Yeah, you're dividing like f of x divided by g of x. So here's the b, here's the b sub 0, the coefficient, the coefficient on the first term can't be 0, so that means that term can't be 0. If that's the case, that's a requirement or you can't do the division. But okay, if you meet that requirement, then the resulting series converges for sufficiently small x values. So this paragraph is kind of ambiguous, but you can, I think it gives you that some direction if you want to do further research on radiuses of convergence, resulting radiuses of convergence after you multiply or divide power series. Okay, let's work some example problems.